Well, hello again, friends. I was asked to do a quick sort of recap on parameterizations of the shoe. I think this is usually questions that pop up now that we're sort of relying on having these parameterizations down pretty solidly, and it would be things that you'd ask me in the hallway or after class or before class or sometime when, we were in the same, zip code, time zone, area, building. I don't know. Anyway, so here are my thoughts about parameterizations of the shoe, just to sort of jog your memory and give you a place to come back to when you have questions about it. So, of course, the shoe, right, x double dot equals minus omega squared x, is the second order differential equation that we see so often in this class, right? It's generically the equation that we get whenever we have near equilibrium physics. And what you always know about parameterizations of the shoe is that at some point we're going to end up with two unknowns, right? Because every physics problem is going to have a set of initial conditions, the initial position and the initial velocity, and therefore any solution to the shoe has to have just two unknowns left over so that I can plug in my initial conditions and get the actual solution as a function of time. And the three solutions that we know of are the transcendental parameterization, where I've written this in terms of the two transcendental functions, cosine and sine, and my two unknowns are a and b. Okay, and that's where we started in this class thinking about parameterizations, and it's a good one, right? Because they're nice and easy, and sines and cosines are things that we are pretty comfortable with. There's also the phase parameterization, and in this phase parameterization, I only have one transcendental function because I've encoded my two unknowns in this overall amplitude d and this phase phi. And depending on how good your pre-calc class was, you know that using double angle formulas or angle addition formulas and things like that, that I can always write a sum of two transcendental functions as one transcendental function with this phase. And so it's not surprising that we can do this rewriting, but this way our two unknowns are encompassed in those pieces of information. What you probably hadn't seen before is the complex parameterization, where my unknowns are really hidden inside this complex coefficient c. Even though I'm going to be taking the real part of this function at the end of the day, the fact that the thing that's oscillating, the complex exponential, is a complex object, both the real and complex parts, real and imaginary parts of this coefficient c are going to play a role in the dynamics of the shoe, right? Because when e to the I omega t has an imaginary part and c has an imaginary part, we multiply those two things together and we actually get a real part. Okay, this is a really useful parameterization. I hope many of you will see it in classes in the future, especially classes like E&M and optics. Okay, so I always start with the transcendental parameterization because to me it just really helps to think about where the physical nature of these coefficients comes from. Right? So if I have the transcendental parameterization, I can see that x is a cosine plus b sine. Of course, the derivative of x is minus a omega sine plus b omega cosine. And the reason I like this is because when I go to my initial conditions, which I almost always set to be t equals 0, in this parameterization, two of these terms just disappear. The two cosines go to 1, and I'm left with x just being a and x dot just being b times omega, right? And so to me, that tells me that in this parameterization, a and b really encode the position and the velocity in a way that's straightforward and easy or fun or something to see. Anyway, but here, those two terms then really represent the information associated with the initial position and the information associated with the initial velocity. Okay. Now, I can do some fancy algebra with this. Sine can be written as a difference between two complex exponentials, and cosine can be written as a difference between two complex exponentials. Plug this in, do the algebra. I get to this kind of fun step here. And for those of you who haven't seen this before, it's sort of a tricky step, but basically the second term here that I've circled in red is actually the complex conjugate of the first term. And it's a nice way to extract the real part of some object by taking that object, adding its complex conjugate, and then dividing by 2. And so I can take this and exactly reconstruct the real part of a minus ib times e to the I omega t. And of course, this is just the complex parameterization, right? And so you're not surprised that I can go from one to the other, where a and b were real, and now a minus ib is what we used to call that complex number c. And I'll probably say this again in a minute, but what I can see directly from here is that a is the real part of c, but b is minus the imaginary part of c. And that's a minus sign that we've struggled with in the past in some of our problems, because I like to think about, those two pieces of information are still there, right? A is still the initial position, which is the real part of c. B is still the initial velocity, or proportional to the initial velocity, but now it really has inside of it, it's minus the imaginary part of c. Okay. So this is what I said a moment ago, but that constant that we called c can now really be identified with the two physical things that we saw in the transcendental parameterization. And so the pieces of information about the initial conditions are still encoded in the real and imaginary parts of c, but there is this weird minus sign that I have to use that tells me that the imaginary part of c is really minus the initial velocity divided by omega, rather than just the initial velocity divided by omega. Okay. Of course, I can go the other way, right? So if I start with the complex parameterization, and I have these two expressions here, where x and x dot are the real parts of the function and the function's derivative. Well, I can solve this at t equals 0, and I see that indeed x naught is the real part of c, and that x dot naught is minus the imaginary part of c times omega, right? So I can reconstruct those just starting from the beginning of the problem. And in a lot of ways, this is a heck of a lot easier than writing down the transcendental parameterization and then moving in the other direction, right? I get this out by just using the parameterization that's best for me, right? And it seems like when I have initial conditions like this, both of these parameterizations seem to be pretty useful. Now, what's nice about the phase parameterization is that I've simplified the number of terms, right? I just have one transcendental function, and of course I know that solutions to the shoe are just an oscillating system. And so rather than worrying about two transcendental functions, I know that it's just going to be one oscillator with one amplitude, and I'm going to take care of the position and velocity by just shifting that to the left or right in time by using this phase factor. And so if I do the same trick where I have I take the function, I take its derivative, and then I solve it for the initial conditions, x naught, x at 0 and x dot at 0. Well, that intuition for a single oscillating function now gives me a system of equations, right? And this is probably why it's everybody's least favorite parameterization, because I can't just say x naught is encoded in one piece of information, right? It's a combination. Where it starts is a combination of the amplitude and the phase, right? And the velocity is a combination of the amplitude and the phase. And in order to solve the system of equations, I need to write down the tangent of phi as being some combination of the initial conditions, and then the amplitude of phi as also being a combination of those initial conditions. Okay? But of course, this solution should not be a surprise to us, because it looks a heck of a lot like trigonometry, right? That if I have those two expressions, that really is the definition of a triangle, where the size of the hypotenuse is d, and then the angle is determined by something like this diagram that I have here, where I'm using the minus sign to define the angle downward, right? So I'm using that notation where when angles go this way, that's in the positive phi hat direction, right? So that this is really a negative angle somehow, because x dot over omega is downward. Okay, but this picture of having the information in the complex parameterization being the angle and the magnitude of the hypotenuse tells me that these two things, amplitude and phase, are really amplitude and angle on some plane, right? Which I can convert very quickly, right, to what I understand of the complex parameterization, right? Because in that case, what I'm doing is I'm taking that coefficient c, which is a complex number, and I'm writing it as an amplitude times an angle, right? Which is what we do with complex numbers. We can either write it as a plus ib, or we can write it as a real number amplitude d times an angle e to the I phi, right? That's that representation. And of course, I can move that I phi in, take the real part, and I get out the phase parameterization. And so, in that way, the complex parameterization really ties everything together, right? There's this real easy connection between the transcendental parameterization and the real and imaginary parts of the coefficients in the complex parameterization. And then there's this geometric picture, once I switch that from real and imaginary to amplitude and phase, that bring us back to the phase parameterization. Okay, so somehow the complex parameterization really ties those things together in a way that's genuinely intuitive. Okay, so I spent a lot of time in the last 11 minutes talking about how to go back and forth between the parameterization, but we also showed during that time how to take a parameterization and then find the two unknowns from the initial conditions. And that's my advice to you. It's wonderful in your mind to know about how all of these parameterizations are the same, right? And how to go from one to another, and how the geometric picture ties into the coefficients. But when I really have a problem, what I do is I look at the parameterization that helps me answer that problem, right? Which means that I genuinely take those parameterizations and then find the derivative, set it equal to my initial conditions. And I do that every time because I don't remember minus signs. I don't remember which way the angle goes. I have to redo it for myself each time. And so my advice is choose a parameterization and just make it work for the problem that you have. Any of the parameterizations will work. So find the one that you like, and as I always say, you be you.